Hey guys, today our topic is silicates or iron silicates. As you know, that the silicon tetrahedrons are considered to be the building block of any silicate mineral. The basic silicate structure is silicon tetrahedra with 4 apical oxygen atoms. The silicon atom, which is much smaller, sits at the center, while the 4 oxygen atoms are sitting at the apex. Silicate minerals are rock-forming minerals made up of silicate groups. They are the largest and most important class of minerals and make up approximately 90% of the Earth's crust. Silica is found in nature as a mineral quartz and its polymorphs that we had already discussed in silicate class. In silicate minerals, these tetrahedras are arranged and linked together in a variety of ways, from single unit to complex frameworks. The simplest silicate structure, that of the mineral olivine, is composed of isolated tetrahedra bonded to iron or magnesium ions. So the silicon atom, which is much smaller, as I told you, if compared with the oxygen atoms, so it sits at the center. Now the 4 oxygen atoms remain unshared in this situation because this tetrahedra do not share its oxygen with any other tetrahedra. So SiO4 tetrahedra can remain isolated with respect to adjoining tetrahedrons or may be linked with adjoining tetrahedra with the help of sharing apical oxygen atoms. When they remain isolated, we call them nesosilicates, which is our today's topic. Here in this diagram, you can see an independent island type of triangle, that is SiO4. Here in the center sits silicon atom, which is surrounded by 4 apical oxygen atoms. Now this tetrahedron shares its oxygen in variety of ways, as I told earlier. Here there is one oxygen sharing, we call it solosilicates. Now here you can see 2 oxygen atom sharing. Similarly, they can share more than 2 or 3 oxygen atom, and in the case of tetrasilicates, all oxygen atoms are shared. But in single independent or isolated tetrahedra, none of the oxygen atoms are shared with any other silicon tetrahedron, so they remain free or they remain independent. Now, a very important group of minerals belong to nesosilicates, that is olivine and garnet, etc. So let's discuss the structure of silicate minerals in a bit detail now. Here you can see these are the tetrahedrons are kind of floating. They are attached with other atoms of different structure, but they are not attached with each other. Here in this red, these could be iron, or this is magnesium. So these iron and magnesium ions are surrounded. So in olivine, Unlike most other silicate minerals, the silica tetrahedra are not bonded to each other. They are, however, bonded to the iron or magnesium as shown on the following figure. I want to show you another diagram which is here. Now one more thing that should be noted is that in mesosilicate structure, this is kind of a 3D model. You can see these are the magnesium ions and this is silicon tetrahedron. Now you can see the position. Not only these tetrahedrons are separated from each other, not sharing their oxygen, but their position is different. Here you can see this, the position is kind of downward, here upward, this front side, here this is the back side. So these are the apical sides, but they are kind of floated in different directions. They are not in the same orientation. Okay, so in Greek, Nissos is referred to as island. The tetrahedron in mesosilicates do not share oxygen. Olivine, which is magnesium iron silicate, and garnet, which is calcium, manganese, iron, magnesium, aluminium silicate, are the most common example of mesosilicates. So let's move to the next slide. Here you can see in this table the common mineral groups which belong to iron silicates or mesosilicates, which were previously known as orthosilicates as well. So isolated tetrahedron or the iron silicates are divided into different groups. So olivine group is the most common one, then garnet group, aluminum silicate group, and other nesosilicates which don't fit in the above four groups. So that's why they are different from these groups. And so let's first start from the nesosilicate mineral groups. Garnet group, here you can see the beautiful picture of garnet. Actually this group, the most important thing I wanted to tell about this group, I wanted to share with you guys that garnet or the nesosilicate minerals are known as the group of gemstones, which has got higher specific gravity, hardness, and the beauty of the gems. Many of them are used as abrasives, but mostly they are used as their prizes, their beauty, and they are used as gemstones. So garnet group, olivine, humite, and aluminosilicates. Though aluminosilicates are a bit different that I'm going to discuss later on. So this is the garnet, the red color one sample is here, though it's found in different various colors. This is olivine, the beautiful grass green color. Then this is humite, brownish reddish color, and the bluish aluminosilicates here. So let's first start with the garnet group minerals. Now garnet group minerals are a group of silicate minerals that have been used since the Bronze Age as gemstones and abrasives. All species of garnet possess similar physical properties and crystal forms, but differ in chemical composition. As a result of the isolation of the tetrahedral groups, the crystal habits of the minerals are typically equidimensional, so that prominent cleavage directions are absent. As you can see in this picture, they are isolated tetrahedrons, and they don't follow a certain direction. That's why there will be no single cleavage direction. Let's go back to the same slide. Now, high specific gravity and hardness, as I told you earlier, are the characteristics of this group, comes from the dense packing of the atoms within the structure. They are densely packed and arranged with other um, atoms. Hardness ranges from 6 to 5 to 6.5 to 7.5. The harder species like alumandine are often used for abrasive purposes. So here you can see the diagrams to make you understand about the structural arrangement of these atoms. Now here in this greenish yellow color, this is the silicon tetrahedron. So SiO4, this red representing aluminium and oxygen here, and this is iron magnesium oxide. So they are arranged in this way. Here you can see them. This is the silicon atom, silicon tetrahedron. This is isolated, though it is connected or it has shared its oxygen, but not with any other tetrahedron, as was the case in all other groups of silicates, in which tetrahedron always shared its 1, 2, or 3 or 4 atoms with oxygen atoms with another tetrahedron, but here it doesn't share any of its oxygen atom. So now the word garnet actually comes from the Latin word granatus, which means seed-like. Uh, it refers to its common appearance of the small, crystals of garnets. They look like pomegranate seeds embedded in the rocks. So reddish color because it's most common one. So red, small, seed-like appearance. Um, has So the small the small seed-like appearance is the reason for the name garnet. The different garnet varieties comprise a group of minerals that all share a similar crystal structure, but whose chemical composition varies as different ions substitute for one another in that crystal structure. Most garnet crystals are actually mixtures of different garnet varieties rather than being composed solely of a single variety. Although red garnets are the most common variety, garnets occur in nearly every color except for the blue. This variability in color results from the garnet's crystal's transparent to translucent nature, which allows minor impurities to greatly affect its appearance. Despite their variable appearances, garnets are usually easy to identify by their hardness, crystal habit, and occurrence in metamorphic rocks, because they are the metamorphic rock minerals. Garnet usually form at high temperature and pressure, so they typically occur in their crystal form as rounded dodecahedron. You know what is dodecahedron? It's kind of 12-sided crystals or 24-sided trapezohedrons. Iron can substitute relatively easily for either magnesium or manganese in the garnet structure, but calcium is a larger ion and does not substitute as freely for iron, magnesium, or manganese. As a result, the garnet group can be subdivided into two series of minerals. The one is aluminium silicate minerals, in which iron, magnesium, and manganese freely substitute for one another, and a calcium silicate series in which chromium, aluminium, and iron substitute for one another. Natural garnets are almost always a combination of these end members rather than being a pure sample of one composition. The general formula for garnet is X3, Y2, SiO4, 3, aluminium, iron, chromium in an octahedral tetrahedral framework with SiO4 occupying the tetrahedra. Now let me explain this formula to you a little bit. The X site is usually occupied by divalent cation, which is calcium, which could be calcium, magnesium, iron and manganese, and the Y site by trivalent cations. So these are the divalent cations, these are divalent cations, and these are the trivalent cations. X is always, now there are two series, andradite series and almandine series. The difference is that in andradite series, X remains same, always same, and which is calcium, right? But Y is variable, this changes. So it could be chromium, it could be aluminium, or it could be iron, depending on that specific mineral's composition. Now in almandine series, Y is constant, it remains same, which is always aluminium or trivalent cations, and X is variable. Sometimes it could be iron, it could be magnesium, it could be manganese or calcium. All garnets crystallize in the isometric system and have dodecahedron and trapezohedron as common forms. Garnet species are found in many colors. As I told you earlier, almost all color is present in garnet except for the blues. So the colors including red, orange, yellow, green, purple, brown, blue, black, pink, and colorless with reddish shades most common. Garnets, the colors depend on the impurities. So the minor amount of the minerals, they can change the whole color of the gems or the gemstones or the minerals. Garnets are usually some shades of red, although grossular. So these are the type of garnets. Is often cinnamon brown, and uberowite is emerald green as a consequences of its chromium content. So here the chromium is responsible for its color. Now let's discuss about the occurrences where these gems are present. So garnets are found, actually they are present in igneous metamorphic and metamorphic rocks, but they are most common in metamorphic rocks. Almandine and spessartine are common minerals in schists and gneisses. The garnet found in metamorphosed limestone is usually grossular. Don't be confused by these names, almandine and all these. We are gonna discuss later on. So these are actually the garnet minerals. Pyrope is a common accessory mineral in ultramafic. Keep in mind, ultramafic rocks such as peridotite, and is also in the derived serpentines. Uberowite, another garnet mineral, also has a peridotitic association where it frequently occurs with chromite. Spessartine, another garnet mineral, is a common constituent of siliceous lavas and complex pegmatites. Garnet has been used as an abrasive, and a good quality almandine garnets are used as gems. Garnets occur in some igneous rocks and pegmatites but are more typical of high-grade metamorphic rocks. Almandine, the iron-rich garnet variety, commonly forms from regional metamorphism of clay sediments and is the most common garnet in schists and gneisses. It also occurs Now, schist and gneisses are metamorphic rocks. It also occurs in silica-rich igneous rocks, such as granite, rhyolite, or associated pegmatites. Pyrope, the magnesium-rich variety, is more common in mafic igneous rocks and metamorphosed mafic igneous rocks, while the calcium-rich garnets, grossular and andradite, are commonly found in metamorphosed carbonate rocks. Spessartine is found in granite pegmatites and metamorphosed manganese-rich rocks, while uvarovite is the rarest garnet variety, only occurring as crusts or seams in some chromia deposits. As garnets are chemically and physically resistant, they often survive the erosion of metamorphic rocks, becoming loose garnet grains. These garnet sands can be concentrated by wave and current action into heavy mineral sand deposits. In most metamorphic rocks, garnets are typically associated with the mica minerals and other metamorphic minerals such as staurolite, kyanite, and sillimanite. Calcium-rich garnet varieties usually form in metamorphosed carbonate rocks, where they may be found with calcite, wollastonite, or metallic ore deposits. Garnet grains in sedimentary sandstone usually occur with other heavy mineral grains or resistant minerals such as quartz. Now, this garnet group includes two series. One more thing I want to add here before continuing, before moving to the garnet series. Garnets are actually the kind of index minerals in a way that the degree to which it has been altered as the different garnets formation and composition reflects the temperature and pressure conditions their host rock endured. That's why garnets tend to record the geologic history of their host rock. Because garnet occur in some igneous rocks and pegmatites but are more typical of high-grade metamorphic rocks. So how much um, okay, so the garnet group includes two series, Paralspite series and Eugrandite series. Now this word Paralspite is actually a combination of three garnet mineral names, which is pyrope, almandine, and spessartine. So this PYR comes from pyrope, AL comes from almandine, and SP comes from spessartine. So this is Paralspite series, which comprises on pyrope, which is magnesium aluminium silicate, and almandine, which is iron aluminium silicate, and spessartine, which is manganese aluminium silicate. The other series, Eugrandite series, is also inspired by three names of these different minerals: grossular, andradite, and uvarovite. So uvarovite, U comes from uvarovite. This GR comes from grossular, and A and T comes from andradite. So this eugrandite series, which comprises on grossular, which is calcium aluminium silicate, andradite, which is calcium iron silicate, whereas uvarovite is calcium chromium silicate. Here are the beautiful pictures of these garnet group. Few varieties of garnet minerals are here. So this is adamantine, pyrope, spessartine, andradite, uvarovite, grossular, and this is another one, rare one is tsavorite and hassonite. Next is olivine group. The olivine series, which shows complete solid solution between magnesium iron and manganese end members and several calcium or calcium magnesium species. All members of the olivine group crystallize in the orthorhombic system. Olivine is primarily an igneous mineral, crystallizing from high temperature magmas. Its two most important end members, forsterite and phyllite, melt at different temperatures, so olivine's melt behavior is similar to that of plagioclase. The general formula for olivine group minerals is magnesium, iron, manganese, calcium, and silicon tetrahedron. So these all or any of them could be present along with silicon tetrahedron. In olivine, divalent octahedral cations occupying two slightly different sites link independent silica tetrahedron. So you can see here these are independent silica tetrahedrons in the bright green color, while this dark green divalent octahedral represents magnesium iron. They are connected with each other and these are the oxygen atoms. Phyllite and forsterite, these are the two end members of olivine group. We are going to discuss it in the coming slides. So, olivine group minerals. This is forsterite, phyllite, tephroite, monticelite. These two are the most common as these are the two end members. Forsterite is magnesium silicon, phyllite is iron silicon, tephroite is manganese silicon, and monticelite is calcium magnesium silicate. The structure of magnesium silicon, the structure of magnesium iron olivine, which is also known as alpha olivine, consists of isolated silicon tetrahedron, which are linked with magnesium iron oxide octahedron. That's what I shown you in the previous diagram. This one. This is octahedron of magnesium iron, and this is the silicon tetrahedron. They are linked together. Olivine changes the structure. Now these are okay, I'll discuss it later about the polymorphs of olivine. Olivine changes the structure with an increasing temperature and depth. At 410 kilometers deep inside the earth, alpha olivine changes to beta olivine, which is known as Wärtsilite. At 410 kilometer depth, alpha olivine changes to beta olivine, which is Wärtsilite. Here you can see this Wärtsilite, which is beta olivine, the polymorph of alpha olivine or the polymorph of olivine. This is actually a synthetic mineral but also found in some meteorites. At 525 kilometer depth, and if you go more deeper, Bacillite changes into gamma olivine, which is known as ringwoodite. This is ringwoodite. This is ringwoodite. So first it is alpha olivine, then it converts into beta olivine, and at a more depth it converts into gamma olivine. Now both has got some interesting fact about it, that both has got the capacity to hold the hydroxyl ion at 660 km. Means if you go more deep and deep, breakdown of gamma olivine to magnesium peroxide occurs. So this only breaks it down. Now phthalate is the iron-rich end member of the olivine solid solution series. Iron-rich olivine is a relatively common constituent of acidic and alkaline igneous rocks such as volcanic obsidians, rhyolites, trachytes, and phonolites. Iron-rich olivine is a relatively common constituent of acidic and alkaline igneous rocks such as volcanic obsidian, rhyolites, trachytes, and phonolites, and plutonic quartz cyanides, where it is associated with amphiboles. Its main occurrence is in ultramafic volcanic and plutonic rocks, and less commonly in felsic plutonic rocks, and rarely it is present in granite pegmatite. It also occurs in obsidian and in medium-grade thermally metamorphosed iron-rich sediments and in impure carbonate rocks. Forsterite. This is the another member and member of olivine, which is magnesium silicate. It is also known as white olivine. Is the magnesium-rich end member of the olivine solid solution series. It is isomorphous with the iron-rich end member phthalate. Forsterite crystallizes in the orthorhombic system. Forsterite is associated with igneous and metamorphic rocks and has also been found in meteorites. Two polymorphs of forsterite are known as wärtsilite, also orthorhombic, that's what I discussed earlier, and ringwoodite, which is isometric. Both are mainly known from meteorites. Peridot is a gemstone variety of forsterite olivine. Pure forsterite is composed of magnesium, oxygen, and silicon. The chemical formula is magnesium silicon oxide. So here are the two pictures of forsterite. Okay, so in olivine group, these are two not so common members of the olivine group are monticelite and christianite, are gray silicate minerals of the olivine group, with compositions calcium magnesium silicates and calcium iron silicates, respectively. Most monticelites have the pure magnesium end member composition. Pure christianite is only found in synthetic system. Monticelite is named after Teodoro Monticelli, Italian mineralogist, which first found this mineral, and christianite, I don't know if I'm pronouncing his name correctly or not, is named after Egon Christian, a German geologist. This is the picture of monticelite. In some basalts, magnesium-rich olivine forms large green phenocrysts in a fine-grained plagioclase pyroxene groundmass. Magnesium-rich olivine is never found in silicic rocks. Iron-rich olivine is found occasionally in some granites. Olivine occurs in some metamorphic rocks including marble and metamorphosed igneous rocks. The next is humite group. These yellow to brown, moderately hard minerals have a layered structure. These are the common humite group members: norbergite, chondrodite, humite, and clinohumite. Okay, so these are the pictures of humite group minerals. This is norbergite, this beautiful purplish color mineral. Then this is chondrodite. Next is humite, and this is clinohumite. Humite group consists of minerals with similar structure, chemistry, and physical properties. The general formula of the humite group minerals is N magnesium, silicon, oxide, or Cs. The general formula of the humite group mineral is N Mg2 SiO4 MgOHF2. Now in this formula, this N is variable. It could be 1, 2, 3, or 4 respectively for norbergite, chondrodite, humite, and clinohumite, while this remains same, but this is variable. Now how is the structure of this humite group mineral? Let me explain it to you. The structure of the various members of this group is essentially one or more magnesium silicate layers separated by an MgOHF2 layer. The structure of various members of this group is essentially one or more norbergite layer separated by olivine layer. So it's kind of mixed with norbergite and olivine, norbergite and olivine, norbergite and olivine. The packing is such that when an N is odd, means this number of these layers of norbergite is odd, not even, the mineral system would be orthorhombic. And when this layering of norbergite, the number of this layering is even, kind of 4, 2, 4, 6, 8, the mineral would be monoclinic. These yellow to brown, moderately hard minerals have a layered structure. The crystal symmetry alternates between orthorhombic and monoclinic for the different values of N. As I told you, orthorhombic and monoclinic, because N varies. And the group contains both orthorhombic and monoclinic species. Chondrodite is the most common member of the humite group. It may contain titanium up to 90%. The humite minerals commonly altered to serpentine or magnesium-rich chlorite and dissolve by weathering, leaving iron oxide residues. Next group is aluminosilicate group. Aluminosilicate minerals are minerals composed of aluminium, silicon, and oxygen. They are a major component of kaolin and other clay minerals. Andalusite, kyanite, and sillimanite are naturally occurring aluminosilicate minerals that have the compositions aluminium silicate. These three minerals are commonly used as index minerals in metamorphic rocks. So these are the three minerals: kyanite, andalusite, and sillimanite. Let me show you a diagram here. You can see this is a phase diagram of this kyanite, this is andalusite, and sillimanite. All three minerals of aluminosilicate groups. group. The aluminosilicate polymorphs very little from end member aluminosilicate and member is sillimanite composition. So uh, there are little slight difference in the or slight variation in the composition. All are isolated tetrahedral silicates but have distinctly different structures. The aluminosilicates are important minerals in paletic metamorphic rocks. The presence of a particular polymorph means presence of any of them indicates a general range of pressure temperature at which the rock must have formed. For this reason, and because they are relatively common, the aluminosilicates are key metamorphic index minerals. They form at different temperature and pressure. Now this is kyanite, sillimanite, and andalusite. These are the polymorphs. Andalusite, which is a low temperature and pressure mineral, so it is formed at lower temperatures and at a lower pressure. So it indicates the conditions which has got lesser heat and temperature, lesser temperature and pressure environment. Whereas this sillimanite is high temperature mineral and this kyanite is high pressure mineral. When the pressure, you can see here the bar is increasing, so it is formed where the pressure condition or the environment is favorable for kyanite. So it is index mineral for reflecting the pressure conditions. This reflects the higher temperature condition, and andalusite reflects the low temperature and pressure environment. These are the different types of minerals. Okay, so these are the aluminosilicates. This blue color is kyanite. Sorry for the typo here. Please read it as kyanite. This one. This brownish reddish color mineral is sillimanite. This one. And this brownish color is andalusite. Starolite and chloritite are important metamorphic minerals in rocks rich in iron and aluminium. Titanite and zircon are common accessory minerals in silicic igneous rocks and in metamorphic rocks. Topaz is most commonly found in pegmatites and hydrothermal veins associated with granite and other silicic igneous rocks. Topaz is formed when formed high temperature fluorine-bearing vapors. Topaz is formed from high temperature fluorine-bearing vapors. The principal use of topaz is as a minor gemstone. Zircon is an accessory mineral in igneous rocks, and because of its high resistance to weathering, it is often found in the heavy detrital fraction of sediments and their metamorphic equivalents. Transparent varieties serve as gemstones. The principal use of zircon is as the one of zirconium metal. Transparent varieties serve as gemstones. The principal use of zircon is as the ore of zirconium metal, most bearing produced from beach sands. Transparent varieties serve as gemstones. The principal use of zircon is as the ore of zirconium metal, most being produced from beach sands. Here are the few pictures of these different minerals like starolite, chloritite, titanite, topaz, and zircon. This is the different colors of topaz, which is also a semi-precious mineral or gem. This is zircon. These are light blue colored zircon, and the whites are transparent or the colorless variety resembles diamond a lot. titanite with a green, beautiful, fresh green color. Then chloritite, which is kind of teal blue or greenish color. Then starolite, which here in this picture doesn't show the transparency of a gem, but there are some varieties which are gem-like. This is a bit about topaz. Topaz is a silicate mineral of aluminium and fluorine with a chemical formula aluminium silicate with a hydroxyl group attached with it. Topaz crystallizes in the orthorhombic system. It is one of the hardest naturally occurring mineral and is the hardest of any silicate mineral. Its hardness reaches to 8. At colorless, if no impurities, it is found colorless if there are no impurities, but could be colorful, as it could be found in blue, brown, orange, gray, yellow, green, pink, and reddish pink colors. So guys, that's all for today's class. Have a very nice day.